So now we come to the second part, which is the classical methods for time series analysis. So it's a pretty long segment, so I will first start with a small overview. So I will start explaining the classical modeling of time series as stochastic processes, right? So random processes. So it's essentially a sequence of random values. And I will discuss central topics like and notions, concepts like stationary, autocorrelation, and so on, which are defined on these stochastic processes, right? So this gives you the basis to understand how statisticians think about time series data. And then I will discuss a number of very central so-called autoregressive models, which are classically used to model the dynamics in time series data. And then I will also discuss what the classical approach is to fit these models to given data. All right. So the classical view of a time series is essentially as an infinite series of numbers, right? And often one assumes that the time points are actually just integer numbers ranging from -infinity to infinity, right? So, I mean, in all practical settings, of course, you don't have an infinite amount of data, but for mathematical considerations, it makes it much easier if you think about it like this. And also the actual time, like the interval between two measurements, that's also something that turns out is actually not that important for all the mathematical considerations. So you just say, okay, so I just have times 1, 2, 3, and also negative times, right? So this is the way that the practical settings are abstracted into mathematics to make the analysis more easier. Okay, and the way this is written down, so here on the slide on the bottom, you have the yt. So these are the measurements, t is the index, and then this notation with the brackets, and the t is an element of this huge z. This is the set of integer numbers. This is sort of just a very compact way of saying the object I'm looking at actually are numbers which are indexed by integer numbers ranging from -infinity to +infinity. So if you read like classical time series analysis books, this is always the first step, is saying that it's a very central assumption about time series is that you have many different kinds of dynamics in the time series, and these are actually additive, right? So usually a way to see this, so let's say these are, let's say, seasonal unemployment numbers or something. So you have different components, and these are given as follows. So you usually assume that you have some general trend, right, which is very long-term, moving very slowly, and often you also assume that it's monotone, so it either always goes up with different speeds or always goes down, right? And this could be, for example, due to economic growth or something. So over time, you just assume that everything becomes larger and larger. And then you have the next component, which is a zt, and these are cycles. But these are not like seasonal, like year-by-year cycles, but more like longer economic cycles, which span, I don't know, a few years. Sometimes it's a bit longer, it's a bit shorter. And then you actually have the season. So this is like year-by-year, right? So for many kinds of time series, let's say, also if you're like monitoring, I don't know, daily usage on a website or so, you have these typical patterns which go up over the day and then go down by night and so on. So this is the next component, and then the final component is noise. Okay, and so if you look at general time series, then there's always this idea that it depends on all of these components. And of course, in order to be able to predict the time series, well, you need to be able to model all of these time series. Although actually, the most of the theory we'll talk about later really just focuses, sort of assumes that everything, that all the trends and all the cycles have already been removed, and just focuses at the raw dynamics of the time series, what's left. So that's something you have to keep in mind. So if you're working with real time series, then actually you have to first usually go through a process where you try to remove these other more long-ranging things, and then you can really focus on the rest. Okay. So for this general time series, and also how this pre-processing is often done, there are a number of simple things you can do. For example, you can compute running means, right? So in order to get rid of the noise that you have on the time series here on the small scale, what you could do is you can compute these running means, and this means that for each time point, right, you're taking the neighborhood of that point with different weighting, and then you're summing this up. So this is the formula here. So for example, the smooth or the running mean at time point t is actually giving as the sum of these 5 time points with different weights, and then you divide by 9, which is just the sum of the different weights, to give you an average. And if you do this, right, then for example, you can get rid of this random part, and then you can really see the seasonal part here. And this is often also used if you want to do the to remove the cycles across years, right? So these runnings means they don't just have to be computed. They cannot just be computed for consecutive time points, but you could also do the smoothing over like the same month each year, and then do this a bit ahead in the future, a bit back in the future, and then that way sort of figure out what is actually the seasonal component here. And there are standardized ways how this is done, which are used by statistics institutions and so on. Okay. Another important, like very simple technique that's often used for removing the trend is differencing. So what you do is you subtract from each time point the value from the time point before, and that way actually you're only focusing on whether you're going up or down, and that's very often if you have a time series which grows over time and you do the differencing, and then if you look at just the difference from one step to the next, you get a time series which doesn't have a trend anymore. Okay, and then like a third very common transformation of time series which you do is that you take the logarithm or the square root of the time series. And the reason for that is often here on the bottom in the middle, you have time series where the noise sort of depends on the values of the time series, right? Sort of makes sense. If the values are 100 or so, then the noise is maybe plus minus 10, but if you're at 1,000, then the noise can get much, much larger. And that's from a modeling perspective also very bad, because you often assume that the noise is sort of stays the same over time. Okay, and one way that's often done is you take the logarithm and then the noise gets much, much more uniform. So for example, for stock prices, you have this. So the larger the stock price, the bigger the variance. You take the logarithm and then it looks nice again. And then there is, so I just put it down here that you've seen this once, is the Box-Cox transformation, which has a parameter lambda. And then depending on lambda, what the value of lambda is, you can sort of smoothly switch between logarithm, square roots, and other things. And this is often some pre-processing that is done. Okay, so this is sort of later on when we talk about the methods, we will never mention this again. So we always assume that the data that we got already has been sort of cleaned for seasonal effects. The cycles have been removed, it has been detrended and so on. Then you can really focus on the data, on the time series itself. So this is sort of the setup. Okay, we have the time series, which is an infinite sequence of numbers. We often assume that the time series has these different components, which have been, and then there are easy ways to do this. So now what we've left with is sort of this time series, which somehow goes up and down and has a bit of noise. Okay, and the classical mathematical way to formalize this is to consider this as a stochastic process. So stochastic process essentially means you have a bunch of random numbers which are indexed over time, but they might also have some dependencies in between. But so the interesting thing about this is that sort of the whole time series that you see is just one realization from the stochastic process, right? So I try to model it down here. So if you have one stochastic process, so not the data that you actually have, but the underlying process that generated the data, so you could go in and then each time get a different time series from the stochastic process, right? And they sort of all look the same because they have the same amount of noise and the same variability going up and down, right? But the whole distribution over possible time series, that is actually the object you're looking at, and the data that you see is just one realization, sort of one draw from this time series. So it's a bit like, so the stochastic process is like a dice, and what you like the time series that you observe is actually what you get from throwing the dice, right? So this the relationship between the two things. And now when the thing you're looking at is this stochastic process, so it's not just the data that you have, but it's a sort of a random time series, and the data that you see is just one realization of that, then you can talk about, okay, what is the distribution of the data, right? So if I would do the measurement many times, so how would the data actually look like? And a very central concept for classical time series analysis is that of stationarity. And stationarity means essentially that the distribution of the time series does not change over time, okay? And this means two things. So one is, so up here I drew the stochastic process, right, the different realization. And now if I take a time point S and a time point T, and here, so this is what I try to draw down here. So you look at the distribution of values at a certain time point, okay, and this gives you this p of y of s, then this is the same no matter what the time point is, right? So if I would do this measurement over and over again today and would do it over and over again in a year, then I would expect that I get exactly the same distribution of values. So this is one part. And the other important part is that you could do the same thing for 2 time points. So this is the plot down here. So you look at time point t, at time point s, right? And then you sort of get a 2-dimensional distribution of points. And usually they will not be, depending on how far these points are apart, they will be highly correlated, right? So because the time series doesn't change that much. So if it's up here and then if I go up by 1 day, actually it will not move too much away. And this means that the points are very highly correlated, and this will not just be like circles, but actually will have some form. Okay, and stationarity in this point means that this distribution only depends on the distance between the 2 time points, right? So the further the points move apart, it might change, and probably points will become more and more independent. But if I do this measurement between now and in a year, and in 6 months, and in a year and 6 months, I will have exactly the same distribution. And these 2 things sort of explain what it means that a time series is stationary. And the way this is mathematically formulated is, so this thing with the distribution, that's already a very strict condition here. And so what you usually say is that if you look at the first 2 moments, so if you look at the average value, the expectation, and the covariance between these 2 points, then they are, so the expectation is always constant, doesn't depend on the time, and the covariance depends on the difference between the 2 time points. A very important statistic of the time series is exactly this covariance. It's called the autocovariance function because it measures the covariance of with the time series with itself given on a certain difference. So this gamma k here, that is the covariance between points which are k time points apart. Okay, and a very closely related constant here is this rho k, which is the autocorrelation function, right? So covariance in general measures if you have 2 variables how much they are sort of moving in the same direction, and the correlation is that but divided by the variance of the variables themselves. So the correlation is a bit like the covariance, but it's normalized to 1. And actually, so if you look at this rho k, then for k equals 0, you get how much a point is correlated with itself, so that's always 1. And then as you make the time difference larger, the correlation goes a bit down. So later on, one of the key things you can do is you can try to estimate the covariance or the correlation from the data, and that is something used later on. Okay, and now there are 2, like the 2 main kind of models for time series data from classical theory are the moving averages and the autoregressive. So we'll talk about this now. Okay, so the simplest kind of model for describing dynamics of time series is this moving averages. So the formula looks a bit like this. Okay, so we have the yt, that is the measurement you make at time point t, and that's given as this epsilon t, which is the noise, IID noise. So IID means it has always the same distribution, and for each time point it's independent, so it's just noise that you get. And then plus a sum of past noise terms with certain weights. Okay, so you could say, so what I get, the measurement I get is essentially a combination of past noises I have seen plus some measurement noise, that is the epsilon t here. And these A1 to AQ, they sort of define what the contribution of these past noise terms is. Right? It's a bit weird to think about, okay, something that you observe is purely made of noise, but why this is interesting is sort of it has a very simple structure. So if you look at the autocorrelation here, so this is the way this is usually plotted. So you have the correlation for the time point with itself, that's always 1, and then as you move away, you're sort of looking, okay, what is the correlation of yt, and then with a point which is k points, time steps in the past. And here, so once you move beyond q, which is sort of the order of the process, then it drops to 0, because all the time points which I get later, right, they are completely made up of noise terms which are independent of what yt is made up of, so they are completely uncorrelated and independent. right? So I would probably not think of this more like it's just some kind of noise, but it's really more a process which has a certain amount of memory, but then it very quickly drops off. Okay, and then the other process, that is the autoregressive process. So I mean, regression generally in data analysis is this idea that you take points and then you try to predict a new point based on the past points, and autoregressive means that you try to predict the time series based on itself, okay? So the sort of formula for the autoregressive process I wrote down here. So it's a bit more, I wrote it in the sum notation, shouldn't be afraid of. So essentially, right, it's just, so what the autoregressive process does, it takes past values, like real measured values, and then it has again weights and sort of combines this together, right? And so, not sure how familiar you are with reading these kind of things, but the thing is, so you always need to look for a pattern. So I always, when I see this kind of like big formula, right, I try to focus, okay, what is the index actually here? So what is actually the part that is moving? And then what are the different objects that go into the sum? And I can see here, so it's moved, the I is moving from 1 to some number. And essentially what I'm doing is, so I'm going through this vector I and taking the different elements of that, and then I'm taking yt and I'm moving back in time, right? And I multiply these together and then I get the sum. So I get like a weighted sum, which is very, very common, right? So the way to visualize this in terms of the time series that's here, so this, let's say this is the yt, the point you have here. These are the previous points, and let's say these are the weights, A1, A2, A3, and essentially you're multiplying this value together with the weight, and you're summing this up, and this gives you the value for yt. Okay, and then there's also some measurement noise, so you always assume there's a bit of measurement noise. The autocorrelation structure for this is already a bit more complicated, right? Because even if you move back a lot, there's always some correlation between the point here, because it never fully drops off, right? So even if you go beyond point P, then the sort of the value, so yt minus p, right? So the point which lies p steps in the past depends on points which lie before that, and even if you move back, there are still points which these depend on. So if you look at the classical autocorrelation function, you can see that very often, so you start at 1, but then it drops off and it goes up and down and so on. So it never really drops to 0. So there's a different, more technical version of the autocorrelation, which is called partial autocorrelation. So I won't go into details how this is exactly defined. But there, for this, you can show that the general idea of partial autocorrelation is somehow you have the autocorrelation, but you try to factor out the correlation you get from the points in between. So you have, like if you go k steps back, then you get the correlation, but you sort of project out the information that you get from the points up to k minus 1, essentially. Okay, and in this plot, so you can show also theoretically the autocorrelation tapers off after p points. So it's not exactly 0, but it's very small. Okay, so these two processes, the moving averages and the autoregressive, these are the sort of the main building blocks of classical theory. And of course, you can combine them into a process which is called the ARMA process. So, and essentially, the idea is that the prediction at time point t has this autoregressive part, and it has this moving average part, and then you have some noise down here. So unfortunately, it's not that easy to say how the parameters here depend on the autocorrelation and so on. So we will later on talk a little bit about how you could use these statistics to estimate what the order of your model is. So one side note here is that not all combinations of numbers actually give rise to stationary processes. So there are some very technical conditions on the AI and BJ, which these need to follow so that you have a process which is actually stationary. And I think the easiest way to see this is that if the AI are very, very large, right, then you have a process which just explodes over time, and that apparently is not stationary. Yes, but I mean, usually all the tools, they will tell you when the process is not stationary, or there are ways to, in the tools we will discuss later, there are ways, if you define an autoregressive process, let's say to sample it, then you can also test whether it will be stationary or not. So just to continue this, so you can already see there's like a lot of, so research has produced like a large number of these different models. And they're all slight variations of one another. So we have the ARIMA process, which is essentially like an ARMA process, but we're doing this differencing, right? I remember where I said in the beginning, if you have a trend, you can often take differences between one point to the next to get something which doesn't have a trend anymore. And the idea here is essentially you have an ARMA process, but on the differences, right? So the idea down here is you have, let's say, something which moves. And now, but if you look at actually the steps up and down, if you just look at the steps, then you have a process which looks pretty stationary, right? So sometimes you go up, sometimes you go down, but overall the process doesn't change. Like the step sizes have always the same distribution. This delta operator here, the large delta, that is what computes the differencing, and you could actually apply this more than once if you want to remove more and more, or if you have a very strong trend. And the ARMA model sort of is an autoregressive model, but on the difference values, right? I mean, if you would want to do the predictions, then you would integrate again, and that's what the I stands for in ARIMA. So far, right, so we discussed through small recaps, so stochastic process, the time series that you see actually comes from a set of random variables, which might be highly correlated, and this gives rise to your data. And you have certain models which you can show produce this kind of processes, right? And usually you have some dynamic in here where the value that you observe depends on a few values in the past. And now, of course, the idea is, so if you now have some data and you don't actually know what the underlying model is, how can you estimate the model? And there's a famous book by Box-Jenkins, I think from the 70s, which they sort of defined the standard program, so the standard procedure, how you should go at this problem of estimating the model. So essentially they describe 3 different points. So first they say you're trying to estimate the order of the model using these autocorrelation or the partial autocorrelation, and then you fit the model, for example, using maximum likelihood. And then in the end, what you do is you test to see whether the residuals, right? So after you make the predictions, you look at the error terms, and then you test whether the error terms are just pure noise, which would then give you that would indicate that actually you learned whatever could be learned, and the rest of the data is just noise. Okay, and then you would do this and then iterate until you have a good fit. Okay, so let's go through these different points and discuss how this is classically done. So the order selection. So as we also from the theory, we know, right, that for the moving averages, the autocorrelation is 0 if we go beyond the order. So what we can do is we can estimate the autocorrelation from the data, right? And then the way this is done is a bit like you would also, so remember that the autocorrelation is closely related to, so it's the correlation between data at time point now and at a time point which is k, has a difference of k, and you can just do sort of take the time series, all this data between all the time points which are now which are k points apart, and then you can take all this data and just do classical estimates of correlation between the points, and then you get a plot. You will see how that looks like a bit later. And then so it won't be perfect, but you can, from that you can sort of say, okay, I guess the order of the moving average process here is this and this number. And then the same thing for a purely autoregressive process, right? So you could do the same thing and look at the partial autocorrelation function and see when it sort of drops to 0, and then it would be a good estimate for that. As I said, for a mixed ARMA model, it's actually not that simple, so you cannot just look at the things. You can sort of start with this to get an idea how good the fit is, but then what people usually do is actually that they look at the resulting, so they see how good the fit actually is, right? What you have to do is you have to add sort of a penalty term to the goodness of the fit, because otherwise the higher the order of the model is, the more power the model gets, and then it can really become really, so usually the error gets smaller and smaller the higher the power of the model. And then there are things like the IEC or the BIC. So these are the Akaike information criterion or the Bayesian information criterion, and these are formulas which sort of are derived from this theoretical setting, and they tell you like if you optimize this function here, so that's a logarithm, this sigma hat squared PQ, that is an estimate of the error that you have left after doing the fit. And then you add this term, and then you can optimize the whole thing over different values of P and Q to find a good fit, right? And then that guarantees that you're not overfitting to your data, essentially. And then just a little bit, so there are different ways how the fit could be done, right? And of course, there are tools which allow you to do this. So I just want to talk a little bit to give you an idea how these kind of algorithms work. So it's like a two-step approach called Hanan-Rissanen. The idea is the following. So the problem sort of is, right, so up here I wrote the ARMA model. So the YTs, that is given as a linear combination of the YTs. So these are things you can actually observe, and then isolinear combination of the error terms, right? And the goal is to get some estimate of these terms, AI and BJ. But the problem is that the only thing that you have actually the YT, so these, but the YTs are already combinations plus the noise, right? So the problem is you don't actually know what the noise is, so you cannot use that to estimate the moving average part of this. And there's one of the approaches that you can do is you take two steps. So first is to fit a purely autoregressive model of a pretty high order on the data. And that gives you an estimate of the noise, right? So if you do this fit via least squares, so you're trying to minimize the square of the errors. And that usually means that you're trying to estimate. So if this works well, then you get a good estimate for the average value of YT. And that allows you to compute the noise term, right? So the way this works is, so you have, let's say if you have 100 measurements, then you take the point of the order, the points in the past, and then you're treating this as a normal regression problem, least squares, and then you get one set of these weights, and then you can use these to compute the error. Okay, and once you have that, then you do a second step where you fit the whole model, but here you're taking these estimated noise terms in to do the estimation. Okay, and then you do these two things, and then you get an estimate of the coefficients of the process. And then in the final step, so for these noise tests, there are different tests which then look at the residuals and see exactly how good the fit is. Okay, but I won't go into details here. Okay, so this is the basic idea, right? So you're estimating the order somehow. This is somehow you can do the fit, and then you get a model out, and then you can look at this. So a bit later on we'll look at Python examples to see how this estimation is done. All right. So before we close this chapter, I just want to give you an idea what other kinds of models have been developed classically. So there are two extensions I wanted to mention, and one is so very often you have data which actually changes a lot in variance, right? So I said before, so if you have the case that somehow the data has a trend, it's moving up and up and up, then you could take a logarithm to somehow try to get the noise back to a normal level. But there's some data, like, I don't know, stock volatility or so, which is just known to sometimes the stock is just moving a lot, and then other times it's not. Okay? And for this, for example, just to give you an idea, there are these ARC models, where ARC stands for autoregressive conditional heteroscedastic. So heteroscedastic means that actually the noise changes over time. And the model looks like this. So the YT is, again, the thing that we can actually measure. And the YT is given as a product of sigma t, which is just a number, and zt, which is IID noise, right? So the YT that we observe somehow is a scaled version of just noise. And the interesting thing is now that for the sigma t, actually we have something like an autoregressive model. So we have noise, which changes from time to time, but the dynamics of the noise variance, that's again governed by an autoregressive model. Okay, and then if you make this, again, you can do the same things. You can do the fit and look at the thing, like how well it can predict your data. And that allows you to deal with this different kind of data sets. Okay, and one sort of the most general version of that, so I mean, what we've seen is always somehow, so we observe something which is sort of a linear combination of some other data plus noise. So same for the ARMA model, but also for these models with the changing variance, right? So it's always, we observe one thing, which is the linear version of something else, and this other thing also has some linear dynamics. And if you sort of generalize this, so mathematicians always like to generalize, you end up with general state space models, which look like this. So there are two parts. So one is they sort of have an internal state, xt, right, which evolves over time in a formula which looks a bit like an ARMA model here. But then already we have the generalization that xt is actually vectorial, so it has more than one value. And that means instead of having this linear combination, we have a matrix vector multiplication here, right? So xt1 evolves to xt linearly plus linearly filtered noise. And then the thing that we actually observe is a linear transformation of this hidden state plus eta t. And then there are ways that you can sort of, all the other models I discussed before can be mapped into this, and you can have a nice general theory of how this works. All right. So this was a pretty long segment. Just to summarize, right? So the classical approach is you model time series as stochastic processes. One key assumption often is that the process is stationary, which means that the distribution for one point, and also if you look at two different points which are a certain number of time steps apart, the joint distribution does not change over time. The classical approaches for modeling the dynamics of a time series are with autoregressive and linear models. And then there are ways to use statistics to infer model order and do the actual fit, and then also check later on whether the fit is good or not. So this was the overview of the classical methods, and next we will start looking at how to use Python to do time series analysis.